In the previous section, we introduced the idea of the power series. Now in this section, we're going to talk about how we can combine different power series together to create new power series. And we're going to look through some of those properties that will allow us to do that. So in this first theorem, it says, suppose that two power series, we have Cn x to the n and dn x to the n, and they converge to the functions f and g respectively. Now, if they have different intervals of convergence, then what you need to do when you combine those is find the common interval, so where they overlap, what they have in common, and that will be the new interval of convergence. So for the first property, this property states that if we have two power series, if we add the two power series together, then they're going to converge to f plus g, since Cn xn converges to f and Dn xn converges to g. When we add them together, it's going to converge to f plus g. And similarly, for Cn x to the n minus Dn x to the n, when you subtract those power series, it's going to converge to f minus g. And then you find that common interval for convergence. Now, for the second property, if you multiply by a power of the variable, so I have a coefficient times x to some power m. Okay, if you multiply that by a power series, then it's going to converge to whatever you're multiplying by times the function f. For the third property, think about this as substitution or composition. Okay, if you have a power series Cn x to the n, and you substitute in for x some power of the variable with the coefficient, then it's going to converge to f of bxm. Whatever it is that you plug in here, you're going to plug in here to see where it converges. Looking at our first example, we have a couple parts here. It says, suppose that we have the power series an x to the n, and the interval of convergence for that is from -1 to 1, non-inclusive. And then we have Bn x to the n power series, and the interval of convergence for that is -2 to 2, non-inclusive. So for part A, it says find the interval of convergence when we add those two series together. So when we add two series together, since we know that they converge, we know that if this converges to f and this converges to g, then when we add them together, it's going to converge to the function f plus g. But then when we're looking for the interval of convergence, we have to look to see what they have in common. So since the interval of convergence for an x to the n is from -1 to 1 right here, and the interval of convergence for Bn x to the n is -2 to 2 right here, where they overlap or what they have in common is going to be where the addition of these two, f plus g, is going to converge. And since they overlap on the interval -1 to 1, non-inclusive, that is where you're going to have your common interval of convergence. Okay, for part B, it says find the interval of convergence for the series an 3n x to the n. So if we rewrite this series using a little bit of algebra and our knowledge of exponents, we can rewrite this as an, and then in parentheses, we can have 3x raised to the n. Because we know an x to the n converges, and we're substituting 3x in here, then we know it's going to converge to f of 3x, which is 1 over 1 minus 3x. Now, to find the interval of convergence, we know that the function 1 over 1 minus x, just the function f, converges from -1 to 1. If I look to see where this converges, I want to take 3x and make sure that that's less than 1. Because when we think about the geometric series, remember that common ratio, that r, needs to be less than 1 in order for this to converge. So I'm going to take the absolute value of 3x and make that, set up an inequality that's less than 1. And then when I solve, the interval of convergence would be negative 1/3, comma 1/3. Now that definitely overlaps with the interval negative 1 to 1, and this is what they have in common. Of constructing power series from known power series. So we're going to use this power series to construct some new ones. Now, when I copied this out of the book, it labeled all the functions as f, and I thought that was a little bit confusing. So I relabeled this as g so that we don't get confused. So we have this function g of x, 3x over 1 plus x squared, and we need to construct this power series based on our mother function here, f of x. So we want to rewrite it in this form here so we can identify what our a and our r values are. Now, if I take this 3x and pull it in front and write this as 1 over 1, and then I change this plus to a double negative, so I have 3x in front, then I have 1 over 1 minus a negative x squared. Then we can rewrite this in this form, saying if I multiply our function by 3x, and I substitute negative x squared in and do like a composition, then this is the case where we're using properties 2 and properties 3 together from above. Let's scroll back up and check real quick. So we're using this property where we multiply something on the outside of f, and then we're also using property 3 where we're using a substitution here. So that means it's going to converge when negative x squared, when this value, my r, the absolute value of my r is less than 1. So negative x squared is less than 1. And when I do a little bit of algebra, we're going to find that that's the interval from negative 1 to 1, non-inclusive. So I just rewrote this in terms of f, so that I could figure out what our interval of convergence is and how we're constructing a new power series given the power series function f. Okay, now for this one, we have to do a little bit more work because it's written with 2 factors in the denominator. So we're going to use the trick of partial fractions to rewrite, I rename this function h, to rewrite h in a way that we can add or subtract 2 functions. All right, so I split it up and I did 1 over x minus 1 times x minus 3 is equal to, and I split it up into its 2 fractions. So I have a over x minus 1 and b over x minus 3. Now, when I went through the process of solving for a and b, and I'll let you guys read through it here on your own, but I got that b is a half and a is minus a half. So I rewrote the function h of x as 2 separate fractions that's equivalent to 1 over x minus 1, x minus 3. So now I need to rewrite each of these in terms of f of x. So for this one, I pulled out a negative 1/2 and then negated it so that I could switch the order down here. Instead of having x minus 1, I had 1 minus x. And so then the double negative made that a positive 1/2. So the 1/2 came out in front, and then I negated the negative so I could switch this order here. And so now it's in the form of 1/2 times the function f of x. So this would be my f of x. Now with the second one, I needed to do a little bit more work. I pulled the 1/2 out and I negated it so I could switch the x minus 3 to 3 minus x. And then to make this 1 minus something, I need to divide everything by 3. And when I divided everything by 3, this is what I got. So now I have negative 1/6 times the function f, and then I use substitution and plug in x over 3. That would be this, where my x normally would be. So I have this function here, and I have this function here, and when I subtract them, I get my h of x. Now, I need to find the interval of convergence for both of these, and then look to see where they overlap. So this here is going to be convergent on negative 1, 1. You can see, you can follow this. I color-coded it so you can see. And then this one, since I know that my r is x over 3, the absolute value of r has to be less than 1 for this to converge. So when I solved for the absolute value of x over 3 is less than 1, I got that this is convergent on the interval negative 3 to 3. Now, when we add or subtract two power functions, we have to make sure that we're looking at the interval of convergence that they have in common, where they overlap. And so if I drew this interval of convergence and this interval of convergence on the number line, where they would overlap would be negative 1 to 1, non-inclusive. So we can say we created this new power series based on f, combining it like this, and we found our new interval of convergence as negative 1 to 1. In this example, we're going to be finding a new power series by doing multiplication with a constant. Okay, so we're looking at this power series here. We have 2 to the n times x to the n. And we know that f of x is our mother function. It's 1 over 1 minus x. That's what we're basing this on. If I rewrite this power function, 2 to the n, x to the n, by combining these, because they're the same exponent, I'm writing 2x in parentheses raised to the nth power. I can rewrite that as the function f of 2 of x. So we're using a substitution here because we're multiplying by a constant, which means when I write this function here, I'm going to have 1 over 1 minus 2x. And to now find the interval of convergence, I want to look to see the absolute value of 2x needs to be less than 1 in order for this to converge. So I set up my inequality and I solve, and I get that my interval of convergence is from -1/2 to 1/2. Now, when we multiply two power series together, we are literally going to be multiplying term by term. If we know that these both converge, so if we know that this one converges to f and this one converges to g, then what's going to happen is when we multiply them, it's going to converge on f times g. And then, of course, we have to find that common interval where they converge together. And just something to keep in the back of your mind. When we do that, this is known as a cauchy product. Okay, so let's look at an example here where we multiply power series. This gets a little bit messy, and I tried to color code it to make it easier for you guys to see. All right, so we're going to take and multiply this power series times this power series. All right, so I'm going to write out up to a certain number of terms, of course. I can't write out all of them, but I'm going to write out each of these power series. So x to the n is 1 plus x squared plus x to the third, etc. And then x to the 2n is 1 plus x squared plus x to the fourth plus x to the sixth, etc. Now, although this is pretty messy, it's not hard. So we're going to do this just like we would normally when we FOIL. Okay, so we're going to multiply. Now I color coded this. I started with red. So I'm going to take this 1 and multiply it by each of these terms in here. And when I do that, this is where I wrote it here. I wrote it out in red. Now, you do notice that I put in placeholders here. Even though we didn't have any x's, I put in a 0x as a placeholder so we could line things up and be a little bit more organized. So I'm going to take 1 times 1, that's 1. 1 times x squared, that gives me x squared. Now, because I didn't have an x term, that's why I put in the 0x, so things lined up. And then I take 1 times x to the 4th, 1 times x to the 6th, etc. And I wrote that all out here, putting in my placeholders for the odd powers. Okay, then I did my next multiplication in blue. So I took x times 1, x times x squared, x times x to the 4th, x times x to the 6th, and I wrote that all out here. Now, of course, it continues, so just keep that in mind that we are only going out a certain number of terms to see what that pattern is. Okay, then I did green next. Green is the x squared term, so I took x squared times 1, x squared times x squared times x to the 4th, x squared times x to the 6th, etc. And I did that out in green here. Okay, and then I did purple, x to the 3rd times 1, x to the 3rd times x squared, etc. And I wrote that out. Now, then I started adding them up. So when I add, this is the only one I have, so I brought that down. I only have 1x here, so I brought it down as 1x. Here I have 2x squared, I brought that down. Here I have 2x to the 3rd. Now here, this is where you have to be a little bit more careful. I see 2x to the 4th here, but if I went out a little bit further, I would find that there's 1 more x to the 4th. So before you add them up, really think about it and make sure that you're not missing anything. If I went out to x to the 4th, and I say I did that in pink or some other color, when I took x to the 4th and multiplied it by 1, that would give me 1 more x to the 4th here. After that, there would be no more x to the 4th, so that would give me 3x to the 4th. And the same thing for the x to the 5th. I only went out so far, but when I went x to the 5th times 1, that would give me 1 more x to the 5th. So that would give me 3x to the 5th. And then I just stopped there and I did my ellipses for the continuation of that. So you can see there's a pattern here. This would be coefficients of 1, coefficients of 2, coefficients of 3. And then if I continued, x to the 6th and x to the 7th would have coefficients of 4. So that's how you want to multiply power series. But just be very careful when you stop multiplying. Just really think hard to make sure you're not missing any terms. Now, since the radius of convergence for both of these series, so for both this one here and this one, they're both negative 1 to 1 non-inclusive. So they overlap at negative 1, 1 when I multiply them together. So my convergence for the multiplication of the two is negative 1 to 1, non-inclusive. All right, now we're going to talk about differentiating power series. And this can be really helpful when you're trying to come up with a new power series. It can be a useful tool. So we are looking at this power series here, 1 over 1 minus x. That's this here. And we want to use this to find a power series for 1 over 1 minus x quantity squared. Now, I notice that this is the derivative of this. So rather than going through and finding a power series for this by using partial fractions and breaking it up, and then finding the sum of 2 different fractions, the power series for each of those, what I can do is, since I see that if I take the derivative of this and I get this, what I'm going to do is I'm going to take the derivative of the power series to get a power series to represent this function 1 over 1 minus x quantity squared. Now, when you take the derivative of a power series, you're literally just taking the derivative term by term. So I'm going to take the derivative of 1 over 1 minus x, and so that means I'm going to take the derivative of x to the n. Now, when I write out all my terms, this is what I've got. When I take the derivative of each of these, this becomes 0 and drops out. This becomes 1 when I take the derivative. This becomes 2x. This becomes 3x squared. This becomes 4x to the third, etc. And it just continues that pattern. So now when I write a power series for this, which is the derivative of this, which would be the power series for function f, when I write out my pattern for that, I get n plus 1 times x to the n, and we know that that converges from -1 to 1, non-inclusive. So this is a lot faster than trying to find the power series for this directly using partial fractions and going through all those steps. Okay, now we're going to use the result of part A to evaluate the sum of this series. So this is what we have. We found that the power series that represents the function 1 over 1 minus x quantity squared is n plus 1 x to the n. Now, if I substitute in for x 1/4, and I can do that because 1/4 is on the interval where it converges. When x is 1/4, this power series converges. So I'm going to substitute 1/4 in for x. And so when I evaluate it, I can see where it converges. So when I plug in 1/4 for x, I get 1 over 1 minus 1/4 squared, which is 1 over 3/4 squared, which I get 1 over 9 over 16. Then I do a flip and multiply, and I find that this series converges to 16 over 9. Now, using that same idea, we're going to integrate power series. So for each of the following functions, we're going to find a power series representation for the given function by integrating the power series f prime and finding its interval of convergence. When I take the derivative of this, I get 1 over 1 plus x, and I can rewrite that as 1 over 1 minus a negative x. Just change this plus to a double negative so it's in a form that we can use. So now I'm using substitution, and I'm plugging in negative x for x. So I have negative x to the power bank. So here is my power series for the derivative of the natural log of x. Now, if I work backwards to integrate it, I get the integral of 1 minus x plus x squared minus x to the third plus ... and then of course we have our dx. So this is going to be, when I figure out what this infinite polynomial is, that's going to be my f of x. So that's going to be my power series for the natural log of 1 plus x. So let's see. So when I integrate this, I get x, and then I get minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4 plus ... Now you'll notice that we're going to start putting our constants in the front when we're dealing with infinite polynomials because we have this ... to show that it continues on forever. So that's why we put this constant in the front here now. So because we have our function, which is a natural log of 1 plus x, and we found that that was this here, okay, our constant plus x minus x squared over 2, etc. Okay, we have that. Now, to figure out what our c is, I know that when I plug in 0, I get out 0. F of 0 is 0 because the natural log of 1 is 0. So if I plug in 0 for x and I get out 0, then this constant here would have to be 0, because if I plug in 0 for all these x's and I get out 0, this constant has to be 0. So we just found a power series for the natural log of 1 plus x by using our knowledge of the derivative and integrating it, finding our value of our constant. And so our power series for the natural log of 1 plus x is going to be negative 1 to the power of n plus 1 times x to the n all over n. That is what we get when we write this in terms of a series. We get this here. And then for our interval of convergence, we're just trying to find the absolute value of x to make sure that that's less than 1. So our interval of convergence is going to be from negative 1 to 1, non-inclusive. Now, using that same trick, we're going to find a power series for inverse tangent. So when I take the derivative of inverse tangent, I get 1 over 1 plus x squared. Now, when I rewrite that in a form where I use my properties of power functions, I have 1 over 1 minus a negative x squared. So for this one, I'm just going to use a property where I use substitution. So when I substitute negative x squared in for x, this is what I get. And now when I integrate each of these terms to work backwards to find a power series for inverse tangent, I get the integral of 1 minus x squared plus x to the 4th minus x to the 6th, etc. And when I integrate this, of course, I'm going to put my constant first now because I'm dealing with infinite polynomials. When I integrate each of these terms here, I'm going to get x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7 over 7, etc. And because inverse tangent of 0 is 0, I'm going to get that my constant is 0. So when I find my pattern for this, and I put it in terms of a series, I get that my power series for inverse tangent is going to be negative 1 to the n, x to the 2n plus 1 over 2n plus 1. And when I find my interval of convergence, I want to make sure that the absolute value of x is less than 1, so it's going to converge from negative 1 to 1. So in this lesson, we have talked about different methods of finding power series for functions. Now, what happens if I use two different methods to find a power series for the same function, and I get two different power functions? Well, what this theorem is saying, it's called uniqueness of power series. If you come up with what you think is two different power series for the same function, that's not going to be the case. Those two power series are going to be equivalent because you can't have more than one power series for a function. So they might look different, or they might be rearranged differently because you use different methods to find them, but in reality, they're going to be the same. So the same idea of, 1/2 is the same as 2/4. They look different, but they're equivalent. So just be aware that every function is going to only have one power series.